The point of the implicit function theorem is to start with some sort of relationship or equation between variables. For example, x squared plus y squared equals 1. And you ask yourself, in a local area, notably in a neighborhood around some point, does one or several of these variables determine another? In other words, is it possible in certain areas of the graph of an equation to reinterpret the graph of the equation as the graph of a function? Now, if we look at the graph of the famous unit circle described as x squared plus y squared equals 1, we know that it's not a function in general because it completely fails the vertical line test. However, if I just grab this point and say I look in some area or neighborhood around this point, then if I zoom in as I've done in this graphic and throw away the rest of the circle, then yes, here we do pass the vertical line test, and we could describe the set of points left in the neighborhood that I've highlighted as the graph of a function of the form y equals f of x. So in other words, if we're just looking at this piece of the graph of the equation that we started with, for each choice of x along the horizontal axis, there's a unique choice of y. So y is determined by your choice of x. This example highlights what the implicit function theorem is going to do in general. Before I state the theorem, let me mention a few key pieces of notation and terminology. I recommend whenever you start with an equation or a set of equations, like we will see later in this video, that you set up what is called the implicit equation first. So in practice, what you do is you just move everything interesting to one side of the equation and rewrite what you start with, in this case, as x squared plus y squared minus 1 equals 0. Then you define a function. So typically, this is a function that you need to bring into the story. It's going to look like a function on all of the variables in question. For this example with the unit circle, the function that I'm going to bring into the story is capital F of x and y equals x squared plus y squared minus 1. I won't take the actual computation here further until we've stated the theorem, but let me mention a couple of other items which are going to come out in the language of the theorem. You may have wondered why I drew a rectangle around the point that I highlighted, and the reason why is because we can view that as the Cartesian product of two open neighborhoods, one on the x-axis, which we will call u, and the other on the y-axis, that one we will name v. So in a moment, when I state the implicit function theorem, under the list of consequences, you will see the existence of neighborhoods u and v, so that when we restrict our attention to those neighborhoods, the graph of our equation can be reinterpreted as the graph of a function. So based on this example, you have an understanding of the capital F function, the neighborhoods u and v that we are about to see. Let's move on now to stating the theorem. We will return to this unit circle example in just a moment. So the implicit function theorem helps us figure out if locally, like in a neighborhood around a point, we can reinterpret the graph of an equation as the graph of a function. Here are the hypotheses that we need. The first few just say that you have a good setup, and then there's an actual test. So the first thing that we want to see is that we are working in a nice open subset of Rn cross Rm, or in other words, R to the n plus m. The dimensions n and m here go with your desired independent and dependent variables. Okay, that will become more clear with examples. Let's move on. You are analyzing your equation around some anchor point, so you need to start somewhere specific. The function capital F, which again you might need to create as we did a moment ago, is a map from your domain, defined in our first hypothesis, to Rm, the desired dimension of your output variable. Again, we will see examples, but keep in mind that capital F will go from a larger space to a smaller space, because we are mapping from Rn plus m down to just Rm. It's at least C1, so at least continuously differentiable. And you've done a good job setting it up if when you plug your anchor point into the function, it sends you to the origin in Rm. Before I move on to the next hypothesis, these first four items are usually very fast to check. This is just saying, are you working in a nice open set at a specific point with a nice function? If you are, then here's the real test. At your anchor point that you have identified, you are going to form an m by m square matrix, whose entries consist of the partial derivatives of f with respect to your desired output variables. What I'm trying to describe will become clear once we've worked through several examples, but it's going to be an m by m square matrix, which means that you can assess whether or not it's invertible by taking, say, its determinant. You want it to have a determinant which is non-zero. It's a very similar test to the inverse function theorem. I want to point out that the implicit function theorem is not an if and only if statement, which means that if this determinant is zero, or you are otherwise unable to meet these hypotheses, then your attempt to use the implicit function theorem is inconclusive. So when you are able to meet these hypotheses, then you can apply the theorem. It's a similar situation that we saw with the inverse function theorem, where again our test amounted to taking a determinant. For both of these two closely related theorems, if the matrix that you are assessing is not invertible, in other words, your determinant test is zero, you have not met the hypotheses needed to use the theorem, so you need to perhaps try something different. If your function f passes this test at your anchor point, then here are the conclusions. The first one refers back to those neighborhoods u and v that I sketched a moment ago, and which we will return to. There exists an open neighborhood u of your desired independent variables. That neighborhood u is a subset of Rn, and there exists an open neighborhood v of your desired independent variables. That is an open neighborhood in Rm, so that for each choice of input x from the neighborhood u, there exists a unique choice of y from the neighborhood v, so that when you plug in that x with that y into your function f, you get mapped to zero. Here, by saying there exists a unique y, what we are saying is as soon as you have identified an x, there is only one way that you could then pick a y. That's like a vertical line test. So that unique choice of y, which unique choice is really a way of saying no choice whatsoever, the y is prescribed for you. That prescription is the action of an implicit function, which we will name little f. So little f says, given the x that you've picked from u, here's the y you must partner it with. Little f returns you a y given your choice of x, so it is a map from u to v. So what is it doing? Is it saying, given your choice of x, here's the corresponding y, which you must partner with that x, so that when you plug the pairing into the function capital F, you get mapped to zero. So there's a rule the x and y have to follow. In all likelihood, f is implicitly defined. It often happens that you cannot write down an explicit form for the function little f, but we do know some things about it. This implicitly defined function little f has the same smoothness as the original function capital F, so it's also CR, where r is greater than or equal to 1. And for any input from the neighborhood u, we can actually compute its Jacobian matrix. So here's the formula for it, but it won't make a lot of sense quite yet because we haven't really seen what these matrices look like. So what's coming next is we're going to work through several examples, starting with the unit circle example that we were looking at just a moment ago. Then I am not going to prove the implicit function theorem in this video because I think it would take me over an hour. So just like with our recent video on the inverse function theorem, we are just going to explore examples with this theorem, and then we will have a separate video where we actually prove that the inverse function theorem implies the implicit function theorem. So we will view it as a consequence of the inverse function theorem. Okay, let's go back to our unit circle example. So we were considering the equation x squared plus y squared equals 1. The graph of this equation is a circle in R2, so it is not at all the graph of a function. It completely does not pass the vertical line test. Let's understand how to check these hypotheses on this example. So first, what are these spaces that we are describing as Rn cross Rm? Here that looks like R cross R. So we think of the first copy as where x lives. That's the copy of the real number line that we're drawing horizontally. And then the second copy of R is where y lives. That's what we've drawn vertically, so that R2 can be thought of as the Cartesian product R cross R. The anchor point is the same as we had a moment ago. Let's move on to the function. I mentioned this already, but the rule of thumb is to take whatever equation or equations you have, move everything interesting to one side so that everything equals 0. That's your implicit equation, and that's how you define the function. So our function capital F that we need to bring into this analysis is capital F of x and y is x squared plus y squared minus 1. Notice it is a map on R2. R2 is open, So the subset A here doesn't need to be a proper subset. And it sends us down to R. F is a function from R2 to R. It's completely smooth. And if we were to take any point on this circle and plug it into capital F, it would send us to 0. So let's move on to the check. Here's what I'm trying to describe with the notation on the left. I recommend that you compute the entire Jacobian matrix for F. So in this case, dF at any point x and y in all of R2 looks like 2x, 2y. From this matrix, which should always be a wide matrix, because F is a map from a larger space to a smaller space, you are looking for a square submatrix which represents the dependence of F on what you want to say is the dependent variable. So dF dy in this case is 2y. This is the 1-by-1 submatrix here that I've highlighted, which means that if the anchor point I've grabbed doesn't have a y-coordinate of 0, we are good to go. So that point we started with will work for us because y is positive. Okay, so to recap, the space you're working in will be R2, the number of variables that you begin with. We began with 2 variables, x and y, so the overall space was R2, which we broke into R cross R. There may be no need to bring in a proper subset called A, which is open. We just stuck with working with the entire space R2. We have a point now highlighted in the first quadrant, which we know will work for the application of this theorem. We defined a function capital F using the implicit equation, and then we tested whether the submatrix formed out of the columns where we've differentiated F with respect to the y-coordinate. We checked if that submatrix was invertible at the point that we highlighted, and it was. Okay, so let's move on to see what the conclusions give us. Here were the conclusions. The first one tells us that if we look around our anchor point, we can find an open neighborhood U of x and an open neighborhood V of y, so that for any input from U, there is a unique output y, satisfying that capital F on that pairing is 0. Okay, so we're working now in the Cartesian product of U and V. That's this rectangle I formed. To help you understand this idea that there's a unique y satisfying that capital F of x and y is 0, keep in mind that capital F is defined on all of R2, not just on the circle. So f of x and y equals x squared plus y squared minus 1 is a function which you could evaluate on the entire xy plane. And what you would find if you started evaluating f on this neighborhood u cross v is that if you go above the circle, f is positive, but if you go below the circle, f is negative. So it's like, if I pick a random x from the neighborhood u, there are infinitely many choices, say below the curve in that box, where capital F would be negative, and infinitely many choices, say if I pick any y value above the curve, for which f would be positive. If I want f to be 0, I don't have any choices though. I have to pick the y value that comes from this curve. That idea, that constraint that I have to pick exactly one y given some choice of x is the definition of a function. Each input is sent to exactly one output. When we plug that pairing into the original capital F function, we get sent to 0. So the second bullet point in this list of conclusions is really like a restatement of the first one, just saying that little f is doing its job. In this case, we actually know what the function is. We can solve for little f of x. It's the square root of 1 minus x squared. You can pause if you'd like to go ahead and compute f prime of x. And before this lecture, if you were going to compute that, you would probably say, okay, bring down the 1/2 power. So it's 1/2 times 1 minus x squared to the negative 1/2 times negative 2x because of the chain rule, and then you can simplify that a bit. Here's another way to get to f prime of x through the implicit function theorem. So here, the Jacobian of f is really like f prime of x. And what we're going to do is say negative the inverse of that boxed quantity up in the top left. So I'm going to invert 2y and then multiply that by, if you look at the symmetry of the notation here, the other columns of the original Jacobian matrix. So here's what it looks like. df, or f prime of x, is negative the inverse of 2y times the matrix, which is just 2x. Inverting 2y is like writing 1 over 2y, the 2's cancel, we get negative x over y. Given that we know that y is literally little f of x, you could rewrite that as negative x over little f of x, and then if you check that against our well-known ability to compute f prime of x for this example, you'll see it's the same thing. We already knew a lot about x and y on the unit circle, so let's look at a similar example where we're not as familiar with the shape in question. Consider the equation y cubed equals the sine of x plus y, which I've graphed for you here. We recognize, looking at the shape that the graph of this equation is tracing out in the xy plane, that we are not looking at the graph of a function because it fails the vertical line test. However, I've highlighted 2 points where I would like for us to use the implicit function theorem. So first, let's start on the left. Near the origin, does this equation determine a function y equals little f of x? In other words, if I zoom in around the origin, do we pass the vertical line test? Can I reinterpret the set of points making the original equation true as also the set of points produced by graphing a function? Let's start by defining the function capital F. Just like before, what we're going to do is move everything over to one side and say capital F of x and y is y cubed minus sine of x plus y. Like in the previous example, this function capital F is a map on R2 to R, where here we want to think of R2 as R cross R. We've obviously set this up correctly, but you want to check f of the origin does indeed get sent to the origin. Our first 4 hypotheses are all satisfied here, so we have a nice function on a nice domain, and the way that we've created this function, if I evaluate it at any point on this blue curve, capital F will send us to 0. So now we move on to the real test. Let's check what the Jacobian matrix of f is at the origin. Because capital F is a function from R2 to R, we should have a 1 by 2 wide Jacobian matrix, and it looks like this. So you compute the Jacobian of capital F in the usual way by computing partial derivatives, plug in the origin, and we get the 1 by 2 matrix, -1, -1. It's the same number, but the column of interest is the second one. So that's this quantity d sub y of f. It's the columns of the Jacobian matrix where we've differentiated with respect to our desired output variable, which in this case is the scalar quantity little y. Since -1 is an invertible number, the determinant of that 1 by 1 matrix is non-zero, the implicit function theorem applies. So let's start mapping out the conclusions now. We are working around the origin, so we want to imagine a little open neighborhood of 0 on the x-axis and a little open neighborhood of 0 on the y-axis, so that if we just zoom in on those neighborhoods, the graph of our equation would look like the graph of a function, and here's what I recommend that you sketch. So if you imagine u on the x-axis going from the left side of this rectangle to the right side, and v, the neighborhood on the y-axis, going from the bottom of this rectangle to the top, then this rectangle is the Cartesian product of u and v. If I just look here, we do pass the vertical line test, and to every x value from the x-axis inside this rectangle, there is a unique y, so that x and y, when plugged into capital F, get sent to 0. In other words, so that we live on the blue curve. The blue curve is exactly the set of points which sends capital F to 0. That's almost all we can really say here. I can't write down what the actual function is explicitly. There is a little bit more I can do though. I can tell you what its derivative is at 0. F prime at 0, using the theorem, is going to be -1 times the inverse of the matrix that we have in the blue box. So that's the inverse of the number -1, that's 1 divided by -1. Times the rest of the Jacobian columns. Sorry for the redundant numbers here. That's the other -1, giving us a derivative of -1. That has a geometric meaning here. It's the slope of the tangent line. Right, so if we imagine that that blue curve was the graph of a function of the form y equals little f of x, then f prime at any point along that curve is the slope of a tangent line. So here I drew a tangent line of slope -1, and you can see it's nicely tangent to the curve through the origin. Fun fact, you could have gotten that all the way back in calculus, just single variable calculus, if you took the equation that we started with and went through and did implicit differentiation. So if you remember implicit differentiation from calculus, it would give you the same derivative. Okay, let's look at the other point now. That's pi 0. That's the blue point I've highlighted just to the right. We're going to have the same function capital F sending us from R2 to R. Take a moment to check all of the other hypotheses. Okay, the first thing to check is just that your function capital F is doing the right thing, so when we plug in pi 0, we get sent to 0. Okay, so we did define the correct function. Now let's compute its Jacobian matrix and plug in pi 0. This time we get 1 and 1. Just like before, the column of interest is the second one. That is invertible, so once again, the implicit function theorem applies. This time, if you look at a neighborhood around pi, you'll notice that you don't actually have to make much restriction there. In other words, around pi, the graph of the equation really does look like the graph of a function, so I'm going to make a pretty wide rectangle here. The implicit function theorem doesn't give you a prescriptive way to make these neighborhoods, it just tells you that such neighborhoods are possible. So here, since we have an image of this function, we're able to create u and v on which the conclusions are true. If I take any x-coordinate from the x-axis inside this rectangle, there is exactly one y-coordinate, so that the pairing of x and y lands on the blue curve. In other words, makes the original function capital F 0. Let's do a little bit more than we did at the origin. So we will estimate y when x is 3. To do that, we are going to take our implicit function, which I cannot explicitly write down, and create its first order approximation centered at pi. For that, I need little f prime at pi. That's going to be -1 times the inverse of the matrix 1 times the other matrix 1. So again, using the formula, it works out to -1. In my opinion, there's a bit of an optical illusion happening here with this function. It really looks to me like our tangent line should be flatter than it was over on the left, but here's the exact same line moved over to the right. So it really is -1 once again. It's just my mind had a hard time believing that until I put the line down. Okay, now with this derivative, we can write down the first order approximation. Centered at 3, it looks like this. This is just your classic linearization process. So in general, it would be little f at pi plus df at pi times x minus pi. In other words, it's like the equation of the tangent line. We know that the Jacobian at pi is really just the number -1. So overall, we get that the equation of that line that we are looking at is y equals pi minus x. So if I want to approximate the y-coordinate that partners up with x equals 3 in order to live on this blue curve, then I'm going to say, well, if y is little f of x, that's like little f of 3. It's approximately the linearization when I plug in 3. Pi minus 3 is 0.1415, etc. It's the decimal expansion of pi. And now I have a question for you. Have I done an overestimate or an underestimate? To answer this question, we need to recognize that x equals 3 is to the left of this point that we've highlighted. Little f of 3 would live on the blue curve, whereas L of 3 lives on the line. To the left of the point, the line is above the curve, so what we've done here is an overestimate. If you are wondering if you could do higher order approximations, like Taylor series type approximations, then the answer is theoretically yes. While you cannot necessarily write down little f of x, you can write down little f prime of x that you could presumably then differentiate to write f double prime, etc. I'm not typically that interested in going further than the first order approximation, but I just wanted to mention that it's possible. Okay, let's do a slightly different example. So I wanted to mix things up a little bit. Take a moment to read this question and then identify those first few hypotheses. So what are the domains that we're working in? Write down the function capital F, etc. What we are investigating is if near the origin in R3, would the graph of this equation be describable as the graph of a function of the form z equals f of x and y. Such a function would be a surface. So the dimensions here are a little bit different. Let's see how your setup went. Notice we are starting in R3. For that, I just look at the fact that we have x, y, and z. When we decompose it into a Cartesian product, it's going to be independent variables and dependent variables. In other words, we're trying to think of z as a function of x and y. So I want to decompose R3 as R2 cross R. Let's move on now to the function capital F that we need to invent. Here, everything is already on one side of the equality, so let's just write capital F of x, y, and z is that left-hand side. X times cosine of y plus z plus 4y plus x cubed plus 2z. Just make sure now that this matches your decomposition. It is a function from R3 down to R. It needs to send us to Rm. In this case, m equals 1. So yes, this checks out. And of course, the way that we've constructed it, when we plug in the origin, we get sent to 0. Okay, let's test your understanding now with the Jacobian matrix of f at the origin. I've gone ahead and computed it. So here I took all the partial derivatives, I plugged in 0 for each of the variables, and I got the 1 by 3 matrix 1, 4, 2. That it's 1 by 3 makes sense. Capital F was a map from R3 to R, and we always expect the Jacobian matrix in this context to be wide. Okay, my question to you is, what do I now need to highlight with a blue box, basically? So what do we need to test the invertibility of in order to know that we can proceed with the implicit function theorem? We need to look at the columns where we have differentiated with respect to our desired output, which is z. So what matters here is that the 1 by 1 matrix 2 is an invertible matrix. Okay, so the implicit function theorem applies. We could just say in words now that we can answer this yes/no question. Yes, near the origin, the graph of this equation looks like the graph of a function. In fact, if we zoomed in, it would look like a surface, describable as z equals little f of x and y, where I have no chance of writing down an explicit form for the function little f. Like in the previous example, I want to also do a sort of first order approximation so that we use this to compute something, but let me also take a moment to do a little proof. I do not know an explicit form for the function little f, for which z equals little f of x and y near the origin, but I claim that I can find its Jacobian matrix. It's going to be that formula, -1 times the inverse of one matrix times another matrix, but I want to prove that for you, just so that we can say we had a proof in this video. Before I do that though, let me just quickly quiz you. What should be the dimensions of the Jacobian matrix which I'm about to compute? The function little f is a map from R2 to R, so it should be a 1 by 2 matrix. That's different than in the previous example, so I just wanted to throw that out there first. Okay, here's how we're going to actually derive a form for this matrix. Capital F, remember, was defined on all of R3, but what we can say is that near the origin, if I substitute in for z this function little f of x and y, it sends capital F to 0. Capital F is not necessarily always 0. Remember that unit circle example, it could be positive, it could be negative. What's special about our function little f is that it sends capital F to 0. That's how we pick the z values to go with the x and y values. So what I want to do now is take both sides of this equality and differentiate them with respect to x. On the left-hand side, we're differentiating the constant 0 with respect to x, we get 0. On the right-hand side, I'm saying take ddx of that expression for f. So sometimes when I write ddx of capital F the way that I've put it here on the screen, students kind of freeze. But remember that for this expression, capital F, it represents that huge quantity up at the top. So you could go through that and differentiate it now with respect to x. Okay, so it's like there is a prescriptive way to take that right-hand side and go through and say, well, what's the ddx of everything? I've seen students kind of freeze when they see this expression, but it's really just like saying, take that expression at the top, x cosine y plus c, etc., and differentiate it with respect to x. Now here's the thing. I'm saying that z has some x dependence. So when I get to the expression plus 2z, it's like plus 2 times dz dx, right? So we have to keep in mind that there's a composition happening here. We need to differentiate a composition. There's actually a very prescriptive way to do it, given the expression that I've left off with. That's with the chain rule. So this is the way to evaluate ddx of capital F of x, y, and z using the chain rule, acknowledging that z might depend on x. Okay, from this chain rule though, let's make some simplifications. dx dx is 1, dy dx is 0. Those are independent variables. So our second line reduces to this. D capital F dx plus d capital F dz times dz dx. I'm actually here going to replace z with little f, so little f of x. Okay, similarly, if we went through our starting equation and differentiated everything with respect to little y, it would be the analogous steps, and we would get to 0 equals d capital F dy plus d capital F dz times d little f dy. Exact same rationale. Okay, I have 0 equals a quantity and 0 equals another quantity. So we have two equalities here relating 4 total items. Let's organize those into a matrix. So the zeros I have on the left-hand side, that's a 1 by 2 matrix, 0 and 0. And on the right-hand side, I have what those are equal to. We can take this 1 by 2 matrix on the right-hand side. Each term has a sum. Let's break this into the sum of 2 other matrices. So I'll give you a moment to read this. So I had a matrix of sums, which I've now written as a sum of matrices. Look over at that second one. Each term has d capital F, dz in common. In this context, that is a scalar. So I'm going to pull that scalar out, but I'm actually going to recognize it as the matrix product of a 1 by 1 matrix with a 1 by 2 matrix. And then our first matrix didn't change. Okay, so on our right-hand side now, we have a 1 by 2 matrix plus a 1 by 1 matrix times another 1 by 2 matrix. Notice that second 1 by 2 matrix. D little f dx, D little f dy. Take a moment to name that for yourself, so recognize that. That is exactly what we are trying to find. That is the Jacobian of f, little f. To isolate it, let's subtract that product to the left-hand side and then multiply everything through by -1. So basically, I'm just rearranging terms now. So this line isn't too hard, but now I need to isolate the Jacobian of little f, and to do that, in this context, I could just divide by a scalar, but to be a little bit more general in how I'm viewing this, I want to think of it as multiplying both sides of this equation by the inverse of the 1 by 1 matrix d capital F dz. And that's what I've done here. And you'll recognize this formula. This is exactly what we had as our final conclusion of the implicit function theorem applied to this context. So I have the partial derivatives of our implicit function, little f, is -1 times the inverse of that blue box quantity. That's the easiest way for me to describe it, but it's the columns that we test first times the other columns. So now if I'm at some point a comma b near 0, 0, what I can say is the Jacobian of little f at ab is equal to that product on the right-hand side evaluated at the correct point. This amounts to a proof of that formula for this one particular case, when we take an equation with 3 variables and recast it as the action of a function where one variable depends on the other 2. You could also actually take a moment, maybe right after this video, to prove the same formula for the cases that we've already seen when we view y as a function of little x. In the proof of the implicit function theorem that I'm going to post as a separate video, I will give you the more general proof where everything is a subcase of the sort of general statement. And it will follow the same train of thought as the computation that we did here. Okay, so let's use this Jacobian matrix now that we've found it. We know that the Jacobian of capital F, the function that we created, at the origin is the 1 by 3 matrix 1, 4, 2. We need to use those terms correctly in this matrix product. The one that we're going to invert is that 2. That's the term that formed our test. And then the other 2 columns are the 1 and the 4. So what we have here is that the Jacobian of the implicit function little f at the origin is -1 times the inverse of 2 times the 1 by 2 matrix 1 and 4. Simplifying everything, we get the 1 by 2 matrix -1/2, -2. Quick remark, notice that z is a function of x and y, and now we can tell you dz dx is -1/2. So that tells us how sensitive z is with respect to x, and similarly dz dy is -2. So we get the partial derivatives of z with respect to x and y. Those are the coordinates of the 1 by 2 matrix that we are looking at. To finish this example, we have been asked to estimate z when x is 0.1 and y is -0.3. For that, once again, we are going to use this first order approximation that comes right out of our knowledge of how differentiation works. Here's the general formula. Near the origin, we're going to say that z is approximately L of 0.1, -0.3. So we approximate the hard function little f, which I can't even write down, with this nice function capital L. What does that function look like? Well, it's little f at the origin plus the Jacobian matrix for little f at the origin times 0.1 minus 0 and -0.3 minus 0. Here's what that looks like. Then crunching the numbers here, we get that z is approximately 0.55. So in our previous example, we approximated with a tangent line. In this example, we are approximating with a tangent plane. So this example was very similar to our previous two examples, just with an extra variable z. So our next and final example will feel a little bit different. Before we do that though, this is a great time to pause and just review what you've seen so far. Then we have one more example, which again will look a little different. Here's our final example. Consider the points x, y, and z satisfying that x squared plus y squared plus z squared equals 6, and also z equals x squared plus y squared. Where can we apply the implicit function theorem to say that y and z are implicitly functions of x? So on a first read through, this example sounds very different from the examples that we were just doing, but pause before I kind of reveal all of the analysis to you and see how far you can take this. I will come back in just a moment and give you some suggestions before we proceed with the rest of this problem. If you were stumped, I just want to give you some things to think about so that you can correct course if necessary before I kind of go through all of the computations. So the first remark I want to make is that we are starting in R3. How would you decompose that based on what we want to be the independent variable versus the dependent variables? And then given where our function capital F that we need to invent should map to, that comes out of that way of breaking down R3. See if you can define capital F of x, y, and z. If you feel like you've done that correctly, go ahead and compute the Jacobian. I will come back in just a moment. There is one way to approach this problem that I did not tell you to think about, but it's what I'm actually going to start with. In this particular exercise, I can actually imagine what the graph of both of these equations looks like in R3. X squared plus y squared plus z squared equals 6 is the equation of the sphere of radius 6 centered around the origin. On the other hand, z equals x squared plus y squared is the most classic looking paraboloid, so here they are. We have the paraboloid and the sphere. The set of points which satisfy both is their curve of intersection. So if you can see this picture as three-dimensional, these two surfaces intersect in a curve. You can actually fully solve for that curve just using multivariable calculus, but let's go back to the implicit function theorem just to understand how to apply it in this context. One of my tips to you was to write down the implicit equations. And it feels like a silly thing to do, but by setting x squared plus y squared plus z squared minus 6 equal to 0, and x squared plus y squared minus z equal to 0, I hope it made it more apparent that your function capital F needs to send you from R3 to R2, and the coordinate functions of capital F, the first and second coordinate, are the left-hand sides of those implicit equations. So the breakdown for R3 that you should have done was to think of it as the Cartesian product of R cross R2, where we imagine our desired independent variable x as living in R, and our desired dependent variables y and z as appearing in R2. Since capital F is a map from R3 to R2, the Jacobian is 2 by 3, and here it is. Take a moment, if you didn't get this far, to identify the 2 by 2 submatrix whose invertibility we need to assess. This example is a little bit more satisfying because it's actually a matrix. So in the previous examples, it was always just a scalar quantity, but here we are looking at the final two columns because this is where we differentiated with respect to y and z. So that is a 2 by 2 square submatrix. We can compute the determinant. After factoring negative 2y in front of the determinant, we can write it as negative 2y times 1 plus 2z. The implicit function theorem will apply whenever the determinant is non-zero. So either y needs to be non-zero or z needs to not be negative 1/2. We never need to worry about that second condition because z is always greater than or equal to 0 when z lives on that paraboloid. But let me give you a geometric understanding of what it's telling us. X is x, right? That's straightforward. Y and z are now being viewed as functions of x as long as we are thinking around a point where y is non-zero. That means x, y, and z are all being determined by a single coordinate x. In other words, we have a one-dimensional object. Now this was apparent as soon as I put up that picture. The set of points which satisfy both of these equations forms a space curve. Geometrically, that makes sense, but algebraically, I want you to recognize that that's what it means here to say that y and z are functions of x. Everything is being determined by a single parameter. So our conclusion, based on the implicit function theorem, is that we could actually parametrize that curve of intersection locally, again, around some point where y is not 0, as having coordinates of the form x, y of x, z of x, or more traditionally, t, y of t, z of t. So the geometry of this problem is what I really want you to take out of it. We are thinking about a one-dimensional curve in R3. So being able to think of y and z as functions of x has the right dimensionality. I'm actually going to keep going with this problem the way that we are solving it using the implicit function theorem, but I want to take a moment just to mention what feels like the better parameterization for this curve of intersection. You can actually just solve for the x, y, and z values that make both equations at the top simultaneously true through substitution, and what you will find is that z is the constant value of 2. Geometrically, looking over at that picture, that curve of intersection, that circle, is happening in the plane z equals 2. And then x and y live on the circle whose radius is the square root of 2. So typically what you would do is describe this curve of intersection as r of t equals the square root of 2 times cosine of t, square root of 2 sine of t, and 2. Here, there's really no restriction on t. If you let t go from 0 to 2 pi, you trace out the entire circle. So I am mentioning this as perhaps a superior approach. But now that we've seen this, let's see if we can kind of connect these two. So could I start with my curve that I've gotten from the implicit function theorem and try to grow it into this better understanding? What I'm going to do is find the Jacobian matrix d little f, where f is the implicit function, allowing us to say that around any point on this curve, where y is non-zero, we can say y and z are little f of x. Okay, so let's do that. Let me give myself a little bit more room here. I can actually give you a point that would work on this curve. You can check the point 1, 1, 2 lives on this curve, but without being too precise, let's suppose that ABC is a point that makes both equations true. In other words, capital F of A, B, and C is 0, 0, with B not equal to 0. Then near this point, we can say that y and z are functions of x, and now I'm going to use that formula for the Jacobian of little f. In a sufficiently small neighborhood around the point ABC, the Jacobian d little f, which in fact will have two coordinates, we can think of them as y prime of x and z prime of x, measuring the rate of change of y and z with respect to x, respectively. This can be computed explicitly. We just use the formula that we've seen several times in this video. So it's -1 times the inverse of the 2 by 2 highlighted blue matrix that we have at the top. There is a quick way to invert a 2 by 2 matrix, and that's what I've done here. It's 1 over the determinant, and then you reverse the entries on the main diagonal and negate the entries on the off diagonal, and then times the other column, 2x, 2x. Okay, let's do some algebra. I can cancel out to negatives. If I pull the 2 out of that 2x vector, it will also cancel with that 2 in the denominator, so that we can write this as x divided by y times 1 plus 2z times the 2 by 2 matrix, -1, -2z, -2y, 2y, times just the vector 1, 1. If you do that matrix product, this 2 by 2 matrix times this 2 by 1 vector, you will get a 2 by 1 vector whose entries are -1 minus 2z and -2y plus 2y. So we'll get some cancellation in that second entry. And in fact, after simplification, this whole expression becomes the 2 by 1 vector -x over y and 0. So if you look at this and think about what each of those entries represents, we are saying dy dx is -x over y. That's actually a separable differential equation. You can separate variables and you get x squared plus y squared is c, but I actually just want to say that that should remind you of the computation that we did in our very first example in this video when we had the unit circle. We found that dy dx was -x over y, and that's not a coincidence here because x and y live on a circle in this graphic. And then our second derivative tells us that dz dx is 0. So in our neighborhood, z is constant. Okay, so this was just a little exercise in algebra. But I wanted to do something useful with the implicit function theorem for this example, given that we already have such an understanding of what this intersection looks like. I hope you enjoyed this look at the implicit function theorem and that you feel confident using it now. In a separate video, I will prove it as a consequence of the inverse function theorem. Thank you for your attention.